recommend reading chapter 1. But, like I said, it is what it is. It's pretty much, basic stuff. And by basic, I don't mean basic programming stuff. Let's go take a look and make sure that that's true. Yep, Introduction to Computers and Programming. Anytime, I've mentioned this before, anytime in D2L where you click on something and it shows a preview of it, go ahead and download it. It's especially true of Word docs and PowerPoints. Okay, why program? What is a computer? It's a programmable machine designed to follow instructions. The programmer is the person who gives those instructions. And that's all a computer is something that follows instructions. The program itself are instructions located in computer memory to make it do something. Now, there were computers in the past before the invention even of electronics. There were mechanical computers. The first thing that you had were mechanical calculators, where you could enter a series of numbers. Let me see if I can find a picture of one of those. Like that. Each one of these, holds a digit.
And then adding 1 to the lowest order. Any one.
And we're not
You
going to
can
actually
simply
watch a
press the
video
start.
over it, but that's a picture of it. And then you could perform some mathematical operation on it. You'd set up some math that you want to do. You want to multiply something by something, and then you turn the crank or something like that, and it would actually perform the operation. And why would you want something like that? Well, by the time the 1700s and the 1800s were rolling around, the needs of math had exceeded what people could do on the fly quickly. Meaning, like, if you were going to be writing, if you were going to calculate, some astronomical value because you were Tycho Brahe and you wanted to, show that, something was a certain number of miles away in the sky or something like that, or you were keeping track of, businesses that were actually starting to earn money by the 1700s and the 1800s, things were becoming, mercantile. So you would want some way of being able to calculate values, and one of the things that you would want to be able to do is to do math rapidly on large numbers, like multiplying two large values together. And the way you did that before you had your electronic calculators is you used logarithms. You would use a logarithm to multiply this number by this number. That's what the slide rules were, that, the stereotypical, the smart student with his slide rule, in order to be able to multiply numbers together before everybody had pocket calculators. But in order to do those logarithms, you had to have tables of, numbers, and you would look up, you grab the logarithm book, and the logarithm book would have all the numbers in it, and then all the logarithmic values of those numbers. And that wouldn't be the only kind of table that you had. Well, somebody had to generate that table. So some poor fool had to sit down and calculate these things, and then inscribe them on a table. And they would make mistakes. The mathematical books is similarly for a complex formula, right? If you had some, equation, a polynomial equation with 4 or 5 or 6 different things, you could create a table of all the possible answers for all the possible inputs. And I'm going to give an example. We're kind of done with Java. We're going to open up a new notepad. Maybe I'll even get up there and write it. Let's see if we can do that. Although the people watching at home aren't going to be able to see this. So I'll instead type it. What if you had an equation that looked like this? 3x squared plus 4x plus 1. And you wanted to write down 100 different values. If x is equal to 0, what is it equal to? Is it x is equal to 1, x is equal to 2, all the way out, to x is equal to 100 or whatever. So if x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, now we're going to do this stuff by hand. We're going to do it in our head. 3 to the power of 0, or, 0 squared is 0, plus another 4 times 0 plus 1. So if we fed 0 into that equation, we would get 1. Now, what about 1? Well, 1 squared is 1, so that's 3 plus 4 is 7 plus 1 is 8. What if we feed 2 in? Well, 2 squared is 4, so 3 times 4 is 12, plus 8 is 20, is equal to 21. What about 3? I'm really probably not going to go much further than this. 3 squared is 9, so 3 times 3 is 27, plus 12 is 39, 40. That's probably enough. What we're going to do is, if I haven't made any mistakes, we might see a pattern here. What's the difference between 1 and 8? It's 7. What's the difference between 8 and 21? 13, right? What's the difference between 21 and 40?
18?
Yeah. 19?
Yeah.
Yeah. All right. Well, let's keep playing like that. What's the difference between 7 and 13? 6. What's the difference between 13 and 19? 6. Now, I'm going to make a little educated guess. Put a 6 there. And what's 19 plus 6? It's 25. What is 25 and 40? It's 65. So, my guess is that if I fed 4 into this equation, I would get 65. We can kind of verify that in our heads if I can do the math. 4 squared is 16 times 3. What is that?
36.
Yeah. Plus another 16, plus another 1. That would have been... I hope it added up to 65, did it?
Yeah, it's 48 is the first part.
Yeah, so 48 plus another 16 plus a 1 is 65. And so just by repeating this process, you know, we can see that this increases by 6 every time. So add 6 to that, that's 31. Add 31 to that, that's 96. And so on. That's 37 and, you know, whatever, you know, 37. You could generate this table really, really quickly by following that process. You could generate it even more quickly if you had one of Pascal's calculators and you could set up this equation and you could just turn a crank and have it generate all those numbers. You know, you turn the crank once and you'd look at the dials and you'd see, okay, you know, it's 31 and 37. So that's one of the reasons that you would want a mechanical calculator in the 1800s. A guy named Charles Babbage invented a device called the difference engine. Why called a difference engine? Well, you saw what I was doing there. In order to come up with a short form solution for this, I was taking the differences between these numbers in order to solve that polynomial. So this is what it looked like. It's insane looking, but it's got all these gears, and you could program it via punch cards. They already had punch cards in the 1800s, but they were used to control complex looms for creating, you know, complex patterns and textiles. And so he decided that if you combine that idea of the punch cards for the looms, and they weren't little itty bitty things like, you know, they used in the 50s or whatever, they were big things, but you put that in there, that would actually be the program. Punch card would. And you would set the gears up, and then you would let it read from that punch card, read your program in, your little mathematical formula, and it would generate, you know, a series of numbers. And he was really ambitious. He didn't even get this one built before he came up with the idea of the analytical engine. And the idea of the analytical engine is that not only did you have something like this, you had another set which represented your data, and then another set of gears which represented the program that you wanted to run. And so you would feed the punch cards in it, they would set those gears, and then you would set your data, and then you had your, you know, your working memory here. And that was a full-fledged computer. It had all the components that we consider necessary to a modern computer. You know, it had what you would call a processing unit, it had a program, and it had memory that it would modify as it ran. Now, did he ever finish that? No, because the milling, the manufacture of these gears was so precise that it was almost beyond the technology of the time to make the brass gears work. Almost. He could have done it, given an infinite supply of money, but who has an infinite supply of money, you know? So he didn't quite get it to work, but his ideas were sound. And subsequently, as an experiment, people have, you know, actually implemented this in the metal. And so, like, if you go to the IBM museum or whatever, you know, science museums or whatever, you'll see these devices. You can see that several people have made them. That's about how big they were. Pretty neat. But that's what a computer is. Well, it's a little bit more complicated than that nowadays. What you have to do is a programmable machine that will follow the instructions, and then you have to have the series of instructions, and then you have to have the person who makes the instructions. Now, he was the hardware dude, and then there was a woman named Ada Lovelace, who was a mathematical genius who became interested in his project, and she wrote all the documentation for it and essentially came up with the first computer programming language. And that's why one of the computer programming languages that you can program in nowadays is called Ada. Poor Babbage invented something incredibly important, and he didn't get a language named after him. There were stores called Babbage's. You know, you could go and buy, you know, games in the 80s and the 90s at Babbage's. So hardware and software. The central processing unit is the thing that runs, and once per clock cycle, it does some mathematical operation. And in order to do that mathematical operation, it's executing upon memory. It's pulling numbers out of memory, doing something with it, and then writing that number back out to memory. So that's your main memory. That's your RAM. You buy an iPhone, and it's got a you know, megabyte of RAM or a gigabyte of RAM in it, and I think gigabyte's too large. And then there is secondary storage. Well, in the olden days, your secondary storage was like a floppy disk, and then it became hard drives, and nowadays it's flash RAM or solid state drives or whatever. Main memory is volatile, meaning that when you turn your machine off, you lose it all, and so it has to be rebooted, and all that stuff has to be copied back into memory for it to run. Your secondary memory is the you know, permanent or semi-permanent one that maintains its state even when you take the power out. And in order to your computer to be of any use, you have to be able to get some input into it. You need input devices. Nowadays everything is touchscreen, but before that we thought of input devices as being our mouse and our keyboard. And there are other kinds, right? There's light pins, you know, or you can hook them up to sensors. You know, you can be sure that cars nowadays have all sorts of sensors, you know. Those are the input devices that they rely upon. And then output devices, stuff that displays, you know. In olden days, it might have been output in the form of, you know, scrolling printer paper, or, you know, producing punch cards or something like that. And then it was really cool to be able to display your information on a cathode ray tube, you know, just pure characters. And then it was even more cool to have a bitmapped display that could show graphics. So the central processing unit has a control unit which retrieves and decodes program instructions and coordinates activities of all the parts of the computer. And then it's got an arithmetic and logic unit, which is the hardware that's optimized for high-speed numeric calculation. I've already mentioned main memory is so-called volatile, meaning that it's erased when the program terminates. It's also called random access memory. The smallest piece of information that a computer can keep track of is a bit, which is a 0 and 1. And a while back, engineers decided that the most convenient way of shuffling bits around in a computer is in packets of 8 bits, which is called a byte. And so your computer has RAM, big stack of RAM. Back in the old days, you know, you might have a computer that had 64K. I had a Commodore 64, an Atari 800, or an Apple, yeah, and it had 64,000 bytes in it. Each byte is identified by an address. The first one is, you know, 0 or 1, and then a 2, and then 3, 4, 5, 6, 7, 8, 9, and so on, all the way up to the maximum number of bytes. Well, you know, kilobytes means 1,000 bytes, and then megabytes are millions of bytes. You know, so in the 90s you had your computer or late 80s that had, 2 megabytes of RAM in it. And that was cool. And now, you buy your computer, it's got 8 gigabytes, that's 1,000 times more. The computer memory capacities have increased at a geometrically exponential rate, which is pretty astounding from the 70s up until now. So here's an example. If we had main memory and we wanted to store the number 149 somewhere, well, we're just making this up, but it got written into that memory address, that byte, 16. And then the number 72 got written into another arbitrary memory address. Now, in olden days of programming, you might be specifying those memory addresses directly. You might say, okay, read this number and put it into memory address 100, and then read this number and put it in memory address 200, and then take those two numbers and add them together and store the results in memory address 300. That would be awfully difficult style of programming, and it was. So, nowadays we use what are known as variables, and a variable is kind of an alias for a memory address. So if we do A is equal to 149, what's really happening is behind the scenes when that code executes, A is tied together to memory address 16, and so if the program says print A, runs out, finds memory address 16, retrieves that value, and prints it out. So secondary storage, non-volatile, retained when the computer is not running or the computer is turned off. You can have magnetic media. Magnetic media ruled from like the 50s to the 2010s and hard disks and stuff like that, but nowadays people use the solid state memory and the flash RAM that's in the phones, right? You buy a laptop, hardly ever does it have any magnetic memory in it anymore. Or you could have optical. You used to buy stuff on CD-ROM, or later, DVDs because they held so much more information. Or flash drives connected to the USB port. Or SD cards, that you insert into certain phones. Those are all examples of secondary storage. Input devices are things that send information from the outside world into the computer. You want to make the computer do stuff, so it needs to be responsive to typing or to touch or to press, whatever. So we could broadly break programs, software. Software is a program that has been created for somebody to use. You have system software that manages the computer hardware and the programs that run on it. The operating system is system software. Like if I pop open the command prompt by hitting, Windows R and I type in CMD and I get this window here. Well, that's a form of system software. The command processor is. And there's other ones, right? I mean, the entire operating system, you could. And then there are applications. Well, the system software could be broken down into the operating system and then the utility programs and software development tools. Visual Studio, for example, you wouldn't call it operating system. It's not controlling the computer. You're using it to write other applications. And utility programs, well, you might want a program that'll format your hard drive, right? Or, do some kind of disk management or, list all the running processes. If I go, and right-click on a clock and show Start Task Manager, I get a list of all the processes. The operating system is managing those processes. And yeah, you could call this application part of the operating system, but it's also a utility program. Then you have application proper, which are the games and the word processing and the scientific applications and stuff like that. Stuff you download from the App Store. Programs and programming languages. Originally, a computer would look something like, if we go past the Pascal calculator and the Babbage's engine and stuff like that, you might have let's see if we can find a good picture of this. I tried and didn't in the last class. Find a nice big one. Yeah. There we go. That's what a computer looked like in the 40s. If you can look carefully at it, what you'll see are there are walls of dials, and there are banks of memory tubes, and then there are these what look like telephone operator, like you saw in the movies in the 30s and the 40s or whatever, how may I direct your call, and plug things in. This was your programming. You wrote programs by patching together things like that. And then your data could be entered in the form of dials. And then the memory was the vacuum tubes, which we can't see, but each vacuum tube, could either be on or off. A 0 or a 1, a bit, as we mentioned. And then you could come up with a vacuum tube that could hold more than one state, right? Because a light bulb could have, various levels of brightness. You might have a vacuum tube that held 4 different states of illumination or something to try to make it more efficient. But a computer like this required a team of people whose job was to just check vacuum tubes to make sure it worked. Because, if you needed like 1,000 bytes, well, we said that a byte is 8 bits. If each vacuum tube is 1 bit, that's 8,000 light bulbs, 8,000 vacuum tubes that this thing is managing. And one of them burns out in your program, and your data is lost or whatever. So these things were a nightmare in order to manage. Interestingly enough, again, the first programmers were women, just like Ada Lovelace in the 1800s. You had hardware engineers who designed the hardware, and then they would hire, during the war effort or whatever, PhD math professors, women, who were capable of understanding the hardware, and then they would translate, the goals, the formulas that the Army wanted, or calculations for creating the atomic bomb or whatever, into the mathematical instructions. So the pictures of the time always showed the men looking important, and then there'd be some women standing around as well, and you might think that the guys are the important ones and that the women, but they were equally important, because you had to have the hardware and then you had to have the software in order to run it. Going back to the idea of bits, if you have a vacuum tube, that's a 0 or a 1. And then you have transistors, and the transistors, each gate on it has a state of a 0 or a 1. That's probably a slight simplification. And then on a magnetic media, you could, like you had a tape or a disk drive. If an area is, magnetized to a particular way, its magnetic polarity is one way, that's a 0. And if it's another way, it's a 1. Or, you have a CD-ROM. And parts of it are burned, pits are drilled into the aluminum substrate with a laser, indicating that, that's a 0 and that's a 1. So programming languages. A program is a set of instructions that the computer follows to perform a task. We start with an algorithm, which is a set of well-defined steps. You want to ask somebody their pay rate. You want to calculate their salary. No. The simplest form of salary, besides just being told that I'm going to pay you $10 if you pick up this rock and carry it somewhere else, is if you have like a number of hours worked, and then you have an hourly wage, and then you have a salary based on those two things, one multiplied by the other. So this would be hours per week, right, in our modern parlance usually. Well, in order to calculate the salary, there's a formula for it. Salary is equal to hours times, hourly wage. But that's not enough information to tell a computer what to do. You can't just say, okay, well, there we go. The computer needs to know what kind of steps are going to be followed in order to get to the point where it can perform this calculation. So we would come up with an algorithm. An algorithm would involve something like this. Get the hours from the user. I'm going to change that informal word get to input. And then input the hourly wage from the user. And then calculate the salary I'm going to change that word calculate to set based on this formula. Salary is equal to hours times hourly wage. And then we would output or display the salary. All right, that's more of an algorithm. Pretty simple algorithm. Maybe it's going to be more complicated. Maybe it's going to open up a file and read a whole bunch of hours and a whole bunch of hourly wages, and it's going to print paychecks, right? Or maybe this calculation needs to be a little bit more complex because they're capable of earning overtime, in which case the formula is different, and it might involve, more complex logic than just doing math. Maybe there's going to be some if statements involved or something like that. Well, what do you know? That's their example too. If we're going to make this algorithm even more useful, just saying input the hours from the user isn't really enough, right? The user's not going to know what to input. We would need to display a message telling them what to input. Display, enter hours. And then input the hourly wage from the user. Display, enter hourly rate or wage. Then we could do that calculation and we could display the salary. Maybe we want to make it a more specific, like you earned, followed by the salary. Better still. Now, this is pseudocode, right? This is not a programming language, but pseudocode is adequate for describing an algorithm. Programming language is an expression of the algorithm written in the precise syntax of that programming language. Maybe we ought to turn this algorithm into real code, just because listening to me lecture is boring. Why don't we go ahead and launch Visual Studio, and we're going to write this application. So I launched Visual Studio. I need to dock it so that it's available to me whenever I want it. So I'm going to pin to the taskbar. Then when I'm ready to go, File, New Project. And I want a C++ application, but I'm going to make it an empty project. Maybe someday we'll experiment with some of the other ones, but let's stick with the empty project. So I'm going to call this Lecture B. That's a pretty boring name. Maybe I'll call it, Lecture B is the project name, but then when I actually add a file, I think I'm going to give it a more clever name like Payroll. So it churns for a little bit after I click OK, makes the project. And I've already told you about and already demonstrated that what that is it's actually a directory with some files that Microsoft uses to keep track of that project. Sometimes they call it project, sometimes they call it solution. Notice that it's a new project, but it's closed solution. It's an interesting twist. I don't know why it's not new open project and closed project. So anyways, we want to add a new file so that we can implement that algorithm in source code. So if you don't see your Solution Explorer, you need to pop it open by clicking View, Solution Explorer. So then add new item. I'm going to add a CPP file. I could just leave it that boring name of source.cpp, but I'm going to give it a little bit better name. I'm going to call it, I don't know, payroll.cpp. Click Add. And now I'm going to type in all that boilerplate that I recommended you save as a file somewhere so you don't have to type it in each time. # include, less than, iostream dot, iostream with not a dot, excuse me, iostream greater than. I'm not going to need strings in this particular one, but I do it as a matter of habit anyways, so # include brace string into brace. And then using namespace std semicolon. That's the first actual line of code. The other two things are what are known as preprocessor commands, which is a macro language. The macro language is not part of the C++ standard, but it is used by C++ programmers. So it has its own standard. All right, and then we need to make a main function. The main function is where the compiler knows the code is going to start. In Python, you didn't have a main function. You just started writing code, right? You know, just right from the get-go. But everything needs to be in a function in this language. So int main, parentheses in parentheses. Maybe the code samples in the book are going to say void rather than int, but we're going to do it old school when all programs were expected to return a value to the operating system. The rest of my boilerplate is going to be the word system, parentheses, quote, pause, end quote, end parentheses, semicolon. And in this language, all of our quotes are going to be double quotes unless otherwise specified. This is called a string of characters, and every string has to be defined with double quotes. Can't use single quotes, unlike Python. And we're going to return 0. That returns a value to the operating system that could be checked if we were running this program from the command line. And the return value could indicate useful information, like if this program ran into an error, maybe it's going to return a non-zero value, so that that could be checked, and we could try to figure out what the error was. Okay. Well, I'm just going to test it to make sure that it's all together. My motto is test early, test often, so I'm going to run it now by clicking on the local Windows debugger. You didn't see me do it, but I hit Control-S to save, but if you don't do that, it'll probably offer to save it, or maybe it'll do it automatically. And it ran for a little while, and it says press any key to continue. Well, my algorithm isn't implemented yet. This is all boilerplate. By the way, this is considered poor form, putting a system pause there. Why? Because that's only for Windows systems. Wouldn't work on Unix, on Linux, on Mac. It's a cheap and easy way of getting it to pause. On the other hand, on those operating systems, you won't be using Visual Studio, and it's Visual Studio that's making these programs disappear as soon as it hits the return. But other computer science classes might tell you to set a breakpoint here instead, and to just run the program and have it hit the breakpoint. I think doing a system pause is just as easy. Okay, well, I'm going to go back to my algorithm. Display enter hours. All right. I wonder if I can get all of this on one page on the screen. Something like that. That'll be close enough. Okay. So cout. That's called an output stream. Cout stands for console out. And you'll only see this syntax in this language, and it's considered pretty quirky and idiosyncratic. Nobody else has ever wanted to implement it in another programming language. But works for C++. Cout, arrow, arrow, enter, hours worked, colon, space. Semicolon. Now that's the output stream. That's how we display information to the screen. Now let's get some information from. And we're going to need to store the data that they enter. We of course need a variable. Unlike Python, we have to declare every variable before we use it. So I'm going to declare a variable called float hours. It's of type float. It's a floating point value. I could give it a starting value if I want, but I don't have to, because the user is going to provide it with the next statement. So CIN greater than greater than. The arrows are going the other way to indicate that data is coming from console input to be stored in a variable. So CIN arrow arrow hours. Semicolon. Now that is pretty idiosyncratic because, you know, in other languages don't type this. You'd use console.read, right? Something like that. Or, you know, if you were using Java, you'd use a different statement, but you'd always put on the left-hand side the variable, and on the right-hand side you'd put the function that is returning that data. But not C++. We use IO streams, and that's how we get the data. If you did this, hours, arrow, arrow, CIN, To make it look more like one of those other programming languages where the variable goes on the left, that's actually a syntax error. So we just have to accept, well, every language has its own syntax and its own quirks. Okay, so we have the hours. What's next? Display, enter pay rate, enter hourly wage, whatever. I'm going to call it hourly rate. So cout, arrow, arrow, enter hourly rate, colon. And then we need a variable to hold that as well. I'm going to make it a float as well because they're probably going to earn like $6.75 an hour, not a whole number, you know, or 1082 or whatever, not just 3 or 10 or 12. So float rate equals 0. And then CIN, arrow, arrow, into rate. Now let's calculate via that formula we have. We're going to need yet another variable to hold the result. May as well make it a float because we want to be able to support partial answers. You know, like I earned 67.35. I really want my 35 cents. So we're going to make it a float as well. Float, salary, or earned, I don't know. I called it salary over here in my algorithm. So float salary is equal to, well, first I'm going to just declare it, and then on the next line, I'm going to perform the calculation. You'll see why I set it up. I could have just done the calculation right on the same line. But in a minute, I'll modify this. Salary is equal to hours times rate. Hours asterisk rate. All right, and lastly, we want to display the results. So cout, arrow, arrow, less than, less than. This week's salary is, end quote, or space, end quote, arrow, arrow, salary, arrow, arrow, ENDL. That's not END1, it's ENDL. And I'm going to test it. That ought to be enough. Alrighty, hours worked. Yeah, I worked 30 hours this week. My hourly rate, 9. We didn't do this pay rate last Tuesday, did we? This is new stuff, I hope. Okay, good. All right, and this week's salary is $295.5. Improvements to be made. We could make it loop, right? We could ask the user if they want to run again, right? Because otherwise they just actually have to run the executable again. Another thing we might want to do is to format the data better with like a $sign and to make it 2 decimal places rather than just 1. 2 places after the decimal. Well, we're not going to do either one of those at this point. What we are going to do is, I was creating my variables in line, the code, rather than up at the top. Once upon a time, in the oldest versions of the C programming languages, you had to declare all your variables up at the top of the code that was going to use them. And I'm going to kind of simulate that just because. You're going to see examples of this all over the place. So I'm going to take this float hours is equals 0 and I'm going to cut it and I'm going to paste it up above that cout command. And the same for that float rate equals 0. I'm going to cut that variable declaration and put it out here. And I have one more. Underneath all that, there was one for salary. I'm going to cut that salary and paste it up there. Why? Because that kind of makes the code clearer in a way. You can look at it, you can look at the top of the function, and you pretty much instantly get a grasp of the kind of stuff that we're going to be doing in it. Hours, rate, salary, okay, yeah, I got it. But to make it even more clear, we would want to document it a little bit. So I'm going to add some comments. Salary calculator. Ask the user for hours worked and hourly rate, and calculates the salary. And I'm going to go ahead and put the formula. I'm going to well document this. Formula. Salary equals hours times rate. Good enough. All right, now I wouldn't even have to look at the code in order to know what it was going to do. But I'm probably curious about the code, so I'd scroll down. We're going to add some more comments still. We are going to document what these variables are. So I'm going to use double slashes after the hours variable to say what it is. Now, in this case, you know, it's a kind of a fairly well-named variable, but hours worked. And then on rate, I'm going to add another comment. Hourly pay rate. And on the last one, I'm going to add a comment for that as well. Salary earned. So we have documented what the program is supposed to do, or this function anyways, this main function, and the data that it is using. But there's some algorithm down here that we haven't documented yet. Now this is a trivial program, right? We can tell what these steps are, but I'm going to document them anyways because it could be considerably more complex. So what is this section? This is the input section. Input hours from user. And the next section, input rate from user. Now notice that these look a lot like our pseudocode, right? We had to input the word input and the word input. I guess we should actually say prompt the user for hours and then prompt the user for rate. I'm going to leave it as is. All right, and then we have another section to document. So I'm going to add a comment above that salary statement. Calculate salary. And then lastly, what's the last thing we did is we displayed the salary. Display salary. Now I've kind of spaced it out a lot, which makes it hard to have the entire thing on one page of code. When I'm writing programs in this class, I may not use as much white space as I did here. I'm going to remove at least a little bit of the white space. You don't have to do this. But there. At least we have one page full of code in an easy to read format so that y'all could follow along and people watching the video could follow along. All right. I'm going to run it, make sure I didn't break it by adding those comments. Hours worked, I worked 100 hours this week. Hourly rate, I earn $100 an hour. Must be nice. Okay, and there we go. Earned $10,000. Alrighty, so I'm going to zoom out for a second. This is what my code looks like. I pretty much want your programs to be documented to this level. What do I mean? I want there to be a comment block. We should have put our name on it too, actually. So I'm going to actually put that. I'm going to cut this stuff right here. No, I'm going to leave it right there. I'm going to add my name and the date, August 23, and then I'm gonna note that this is part of lecture B. That's enough of a comment block. But I've tagged this as my own. You could put your whole name and the year as well. I have described what the program does. I have commented the variables, and I've commented the major sections of code. I'm going to paste this into our notes as a sample program. So please document, comment, same thing. I'll change that word to comment. Please comment your program to this level of detail, which is comment the variables, describe the purpose of the program. You could probably just copy and paste from the instructions, right? If I'm giving you an assignment, describe the purpose of the program. And comment the major blocks. Input, calculate, output. Pretty much I want those things in it. When you're a professional programmer, the better you comment your code, the more your coworkers will like you, the more you'll be able to understand your code when you put it down for a year and then you come back to it. Trust me, if you look at code that you've written several years ago and you haven't commented it, it's going to be very difficult to follow. And it's even worse if you get somebody else's code and it's not commented. Real production code, not these sample ones that we write in class, is complicated. It's going to be like lines and lines and lines of code. And the syntax is going to be more arcane than the stuff that we're doing here, and the processes that they follow is going to be more arcane. And if it's not commented, you're not going to have much of a clue as to how it works. So the guys who wrote the program Quake, like the sequel to Doom or whatever, the first-person shooter, they took their graphics library and they licensed it to other video game makers. And you can be real sure that they commented and they documented that graphics library so that other people could use it. If they hadn't done that, if they hadn't provided the documentation for it, then those people wouldn't be able to use it, and they wouldn't have made $1 zillion selling that to the other game companies. I didn't ask if everybody got this running. Did anybody get any syntax errors that you want help with? You all good? Okay. Wait. I guess I closed it. Okay, now here's another point I want to make. Say I have a source code file. I'm going to just upload this, and then I'm going to download it. I'm going to go ahead and make a directory out in D2L. Since we have one for every day anyways. B. Payroll. Calculator. Alright, now there's a reason I'm doing this at this stage, because I want to demonstrate something that's going to bother people at first. Which is, how do you edit the program once you have uploaded it? Or if somebody gives you some C source code, C++ source code, how do you actually get it to run? So, I've got my nice little program. I need to remember where I stored it, so I'm going to do that business about right-clicking on I need a Solution Explorer. Come over here, right-click on it, open folder in File Explorer. I can drill down and find my .cpp file. That's the one that I'm going to upload. feel free to do this, or go ahead and wait until the end of class. Maybe we're going to change the program as we lecture a little bit more. So I go to assignments, I find the upload folder, la da 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 da. I should have had something already set ready to download. I'm going to add a file, add from the computer. I'm going to use drag and drop to get it over there. Add, submit. All right, now I'm good. Now say you did that at home, but then you want to come back in and you want to show me your code. Something wasn't working right, so you want to download it on your workstation. How are you going to do that? Well, I'm just going to click on the submissions. Where's my file? Here it is. There's my payroll.cpp file. I'm going to download it. I'm just going to download it to my desktop and be done with it. Okay, great. Now I'm going to go to my desktop and I'm going to run it. I'm going to open it up and run it. And it's not going to work. Where's my CPP file? Payroll.cpp. I double click on it. Oh, right. There it is. Let's run it. Since it's the same code as I already had going, this is not a good example. So I'm going to switch gears and open up another file that I had written in the past. Go and find one of my old C++ directories. Why don't I just find one in Visual Studio? All right. Here's a program. I just downloaded it from B2L, just pretend. I'm going to run it. Enter hours worked. This program didn't have anything to do with hours. This was about, I don't know, arrays and stuff like that. Didn't have anything to do with hours. Oh, well maybe it's because I have payroll.cpp open. I'm going to close that. I'm going to run it again. Enter hours worked. Well, dadgummit, I'm going to rebuild it. Rebuild solution. I'm being a little bit overly dramatic. I'm a drama queen. So here we go. Enter hours worked. Why is it doing that? Well, okay, I must still have the project open. We're getting closer to the solution there. I'm going to close the solution. Well, it lost my file. All right, I'm going to open my file again. And now I'm going to run it. I can't. All I have is this attach button. And if I click attach, nope, that sure isn't going to work. The problem is that Visual Studio will only compile and run code that is part of a project. That means that you have to have a project. You'll probably make a new one. Okay, so I'm going to make a new project in order to be able to run this. File, new project. I'm just going to call it project 3, I don't care. And then what am I going to do? I could make a new source file and copy and paste. You know, I could do file new, add new, and then I could copy the stuff out of that other one and paste it into here. Or I could do add existing item and go and find that July file. It just depends on whether you want to be editing the one that you just download or if you want to edit a copy of it. That's up to you. All right, so I did add existing. And now I have a CPP file. Well, that was a bad choice. It's not actually one that I wanted to get, so I'm going to choose a different one. But that's how you do it. That's how you do it. You either create a new file, you have to create a new project, and then you either do new file and paste into it, or you do add existing and choose your old one. So if I gave you a .cpp file and I wanted you to run it, that is what you would have to do if you're using Visual Studio. Otherwise, you could compile it from a command prompt, from a shell prompt, but we're not going to be doing that for a while. Okay. Does that make sense, guys? If you have a CPP file, you're not just going to be able to open it in Visual Studio. Make the project, and then copy and paste, or do add existing. All right, so we've implemented this algorithm as a program. All right, so although the previous algorithm defines the steps for calculating the gross pay, it is not ready to be executed on the computer. Now, a computer only executes machine language instructions. Well, what does that mean? And I apologize, guys, for those of y'all who took my fundamentals class and have already sat through the lecture that I'm about to give you. But not all of you have. So what I'm going to do is I'm going to pretend that I'm a computer. Well, I'm going to come up with a computer. I have a little dude in a box. Little guy in a box. His name is Chip. Yes, I'm very clever. You're allowed to laugh now. And Chip has an infinitely long piece of paper, or well, at least it's, you know, maybe it's got 1,000 blanks on it, 1,000 lines. 0 to 99999. All right. And he can reach out to a hole in the box, and he can write on it, right? He can write on the piece of paper, and he can read. So that's our little pencil. That's kind of stupid looking. You get the idea, right? He can read from the scroll, and he can write to the scroll. And he also has a little tablet inside the box, right? Because he doesn't want to have to reach out just to, you know, write everything. So he's got, you know, a little yellow tablet in here. And he's marked off things like, he's put in a couple of comments on his tablet, R1, R2, and R3. And he's going to write some things in his R1 line on his yellow tablet. He's going to write some things into R2, and then he's going to write some things into R3. And there's a reason why I chose those. But anyways, okay. What we're going to do is we're going to tell Chip to do something. We're going to give him some instructions. But we're not going to have nice fancy words like main and set and print and see out and stuff like that. We're going to come up with a little set of what are known as opcodes. And opcodes are instructions that Chip understands. We're going to come up with opcode 10. Opcode 10 means read. Pretend that's an R and you can read it. And then opcode 11 is write. And you electrical engineers don't laugh at me because I'm going to make this example simple and it's not going to be, you know, 100% accurate. But spiritually, I hope it's good, close enough. All right, and then there's going to be another one called add. That may be enough. Maybe we could write a little program based on this stuff. And let's make this multiply so it's like our payroll program. We have another instruction called multiply. Okay, so we're going to write a program. It's going to say 10 is 3 R1. Now all of these would actually be represented by numbers as well. Kind of cheating by giving, you know, letters. And we could get rid of that and just assume that the first number is always the address and that the second number is always a register. But I'm going to go ahead and give myself a little bit of cheating there. So we're going to read from address 3 into R1. And then the next instruction we're going to give him is going to be read from address 4 and store it into R2. And the next command, we're going to multiply R1 and R2 and store the result in R3. And then the next thing we're going to do is we're going to do a write from R3 into address A5. Something like that. Or maybe back into A3. We're going to add one more instruction, 20, which means jump. And so the last thing he's going to do is he's going to jump back to the first instruction. Jump to the top. Like you can read that. Okay. And he's got a clock. He's on the clock. Every second he checks his list of instructions. We give him this list of instructions. And he performs one of the operations on it. So the first thing he's going to do, what's a 10? It's a read. Well, we don't have any data yet, so I'm going to write some data down. And I know the pronunciation's data. Okay, let's say the address 0, address 1, address 2, address 3, address 4, address 5, and somehow let's say that we already have some existing data to play with. And out in address 3, there was the number 6. And out in address 4 is the number 5. Okay, so the first block, first second. Opcode 10 is a read. Read from address 3 and write it into R1. Okay, I'm going to make these boxes bigger. That's R1, R2, R3. So what was at address 3? A 6. The next second goes by. He has to do a new thing. So he reads from address 4 and writes it into R2. Address 4 had a 5 in it. Another second goes by. Alrighty, we're going to do command opcode 12, which is multiply. So we're going to multiply these two registers and store the result in the third register. I changed words midstream, registers being these things that he can read to and write from that are inside his box. So 6 times 5 is 30. And then the last, well, second to last, what's opcode 11? Write. We're going to write from R3 out to address 3. So this no longer contains a 6, it contains a 30. Another second goes by. He follows the instructions, which is jump back to the top. This is the next instruction he's going to perform. So he's got an instruction pointer that he's keeping track of that tells him which instruction he has performed. And so he knows what the next instruction is going to be. And each tick of the clock, he performs another operation. Well, he jumped back to the top, so the clock ticks again, he's got to do it again. He's going to read from address A3 into R1. Well, address A3 has now got a 30, so okay, we have a 30 there. And then he reads from address 4 into R2. Well, 4 didn't change, it's still a 5. And then he multiplies R1 times R2 and stores the result in there. So 30 times 5 is 150. And then he writes that one back out to this memory. He's got 150 here. And then he jumps back up to the top. And he repeats that over and over. And then, I'm not going to do that anymore. Well, that's our computer. Here's the central processing unit. Here's the CPU. Here is the internal memory, the main memory. We haven't done any secondary storage. Let's say that he wanted to write these results down. He might have, say, another strip of paper that he was going to write. This is his temporary memory, his RAM, and the other one would be, his secondary storage, the disk drive, or something like that. These opcodes are the programming language that the chip understands. And every major architecture has a different set of opcodes. Motorola chips act one way, ARM chips act another. Intel does another one. So that's our man in the box. That's how, conceptually, at the most fundamental, my explanation of a computer. We are about done for today. I want to give you some homework based on what we've done so far. And so our homework is going to be just the same kind of thing as we did here, where we're going to ask for some information and we're going to perform a calculation and we're going to display the results. And so the simplest examples that always come to my mind are just like conversions, converting, from ounces to pounds and stuff like that. So, homework, part A, ounces to pounds. Ask the user to input a number of ounces and then calculate the number of pounds and then display the results. Look up the formula. If you can't figure it out, text me and I'll give you the formula. Part B, yards to meters. Same business. Write a program that lets the user convert yards to meters. And then part C, miles per hour to kilometers per hour. Write a program that lets the user convert MPH to KPH. And again, for all of these, look up the formulas or text me for them. No shame in asking me. Not a math class, it's not a physics class. You don't have to memorize formulas. I'd be glad to give them to you. All right, that makes sense? You think you can do that based on our example? You're just going to use some CIN statements to read into variables, and then you're going to have a formula that calculates a response and now a result, and then you're going to use Cout to display it. Now I'm going to make this due Wednesday night, so I would recommend you work on it over the weekend so that if you get stuck, you can ask questions about it on Tuesday. Also, you can always text me. Are we good? That makes sense, guys? All right.
Upload that to D2L, or do we need?
I'm absolutely going to upload it to D2L.
Are you gonna post it as one of the news items or whatever?
Well, where does the homework show up? The homework gets posted in two places. One is there's going to be a Dropbox for it, and you'll see an attachment there. The other is under the contents menu. You'll see a folder called homework, and it'll be posted there as well. So usually I'm not going to post a notice about each homework assignment unless it was something I assigned not in class, right? And I wasn't telling you about it in class. That makes sense? All right. Well, have a good weekend, y'all. And I'll see y'all on Tuesday. If you have any questions, I don't have to leave. You know, we can hang out and talk.
The homework 0 just asked to take a screenshot of a printout thing, and on Xcode, it just basically is the template is a printout hello world thing.
Yeah, right.
Is that okay?
That's fine. Right. Just take a screenshot of whatever C++ environment you have or that you installed.
Okay.
That's really enough. Oh, that's right. That is correct, except it says pause, command not found. And the reason why pause doesn't work is because that's a Windows command. So just comment that out if you need it. You don't ever need to do that. Right. The return is good, right? All right, gang. See y'all next week.